Hey, now we're looking at Unit 10, Differential Equations and Slope Fields. Going to start with slope fields, which corresponds with section 6.1 in our textbook. And differential equations, maybe you'll hear this referred to as DiffEq. That's usually corresponding with Calculus 4 in an undergraduate program. Going to start with slope fields, which are a way to visualize differential equations. So differential equations are equations first and foremost. There's inputs and there's outputs. And it's an equation, not a function. So one input can have more than one answer. But starting with a differential equation, y double prime minus y equals 0, try to determine whether these three given equations are solutions to the differential equation. So we already have y given to us. The equation highlighted in blue requires y double prime. So let's work our way down to that. Y prime equals cosine of x. Y double prime equals, okay, careful, derivative of cosine, negative sine. Checking my notes just to make sure. I make that mistake far too much. So now plug those both in. So negative sine of x for y double prime minus sine of x. And then does that equal 0? And we find negative sine minus sine, negative 2 sine of x, and that does not equal 0. So, no, this is y equals sine of x is not a solution for this. Now, some things you can discover. Okay, some patterns, like y double prime minus y. There's no other coefficients, no other variables being multiplied in or introduced. So look at our three cases. Sine, its derivatives all kind of cycle through the same values. Sines, cosines, positives, negatives. E and E, those also kind of cycle through the same values when you're finding derivatives. So one thing you can do to kind of notice the pattern is to say, hey, is what I'm taking the derivative of going to give me relatively the same output for y prime, y double prime, y triple prime? And now slope fields. These used to be a more popular item on the AP Calc exam. They kind of took a seat on the back burner for a while, but now I've seen them a few more times in recent history on the FRQ portion where you have to make one, or in the multiple choice where you kind of identify which of these choices is represented by this slope field. But it's important to remember, dy dx is a derivative. When you think derivative, think slope. So at any x or y value, the slope will be given by negative x over 2y. So let's start creating a slope field, and you'll just start by working on the axes. So let's start with the x-axis. Now on the x-axis, every point has y in common. Every point at the x-axis, y equals 0. if you plug in 0 for y in your slope equation, you get 0 in the denominator. So dy dx at y equals 0 is undefined. On the slope field, any points that have an undefined slope, you don't need to put anything in for those. You can leave the x-axis blank, okay? Now let's go to the y-axis. On the y-axis, every point has x in common. X is 0. And when you plug in 0 to our slope equation, negative x over 2y, slope will always equal 0. So at every point at the y-axis, except the origin, because the origin is shared with the x-axis, x-axis is already undefined. So at every point at the y-axis, put a little horizontal kind of hash mark. Because at the y-axis, slope should be 0, so horizontal line. And then go by quadrant, filling it in. So we'll start with Q1. So we have the point 1, 1, the point 1, 2, the point 2, 1, and the point 2, 2. So then we're going to just plug all these points into our dy dx equation. Do some very simple arithmetic and get our answer. I don't know why I said -1. It's too early. Negative x is 1. Down here, 2 times y, which is also 1. So -1 over 2 times 1, more commonly known as 1/2, or -1/2, sorry. Again, early. So again, negative x over 2 times y. So -1/4. The point 2, 1. Did again, plug in 2 for x. Plug in 1 for y. Get -2. Nope. Math. Always the bane of my existence. -2 over 2. -1. Duh. To go 2, so -2 over 2 times 2. -2/4, or -1/2. Now the -1 slope, pretty simple to draw, just a 45-degree diagonal line at 2, 1. So kind of put a 45-degree decline on that hash mark. For the fractions, -1/2, -1/4. So usually they're going to grade the zeros and the positive -1 slopes. Those are 1 point together. Gotta get those. And then 1 point for all of the other fractional slope values. Here's what they're going to do. They're going to look at all the fractional slope values in relation to each other. So like a 1/2 should be more steep than a 1/4, more steep than a 1/8, more steep than a 1/16. Okay, so it's not important that you're exact. It's important that in relation to each other, all of your slope values look accurate. Okay, so 2, 2, -1/2, kind of do my best to do a 1 down, 2 over. at 1, 1, there's also negative 1/2. So kind of, you see how there's a 0 slope on the y-axis and a negative 1 slope at 2, 1. At 1, 1, I want negative 1/2, so try to go exactly between those. So try and do a negative 1/2 down 1 over 2. 1/4, negative 1/4, it should be more shallow than negative 1/2, but at the same time more steep than the 0. And that's kind of too close. Let's go there more. So they're not perfect, but in relation to each other, you can see kind of how any curves are gonna start horizontal and then curve down. Okay? So go ahead, finish the slow field, check your work with my notes online, see how you did. Part B requires you to get the slow field completed, so do that also. Part C, I'll show you kind of how this works. And this is going to be a pretty big theme throughout this unit, finding a particular solution. Remember, indefinite integrals find general solution, the plus c. So the plus c says, so where are we vertically placed on the coordinate grid? Particular solution says, well, vertically we're placed right here. We find a value for c. So first we need to start by separation of variables. We have dy dx equals negative x over 2y. So when you take implicit derivatives, dx's go with x's, dy's go with dy's, dh's go with h's, d whatever goes with whatever variable. So we need to get those back together. So do a little cross multiplication. Cross multiplication. Multiply both sides by dx. Multiply both sides by 2y. I'm kind of mudding up my work. Sorry about that. So I said what I meant. I did not write what I meant. So the dx is cancelled. Dy equals negative x dx over 2y. So now multiply both sides by 2y. So you have 2y dy equals, those cancel, negative x dx. And now you do your anti-differentiation. So now take, in red, I want red because they do. Now take your antiderivatives. So 2y dy, 2y will become y squared, and the dy would go away. Negative x becomes negative 1/2 x squared. And don't forget, you need plus c. Indefinite integrals, you need the plus c. Now, you could do plus c with the y also, but then you combine these c's, you just have the 1c with the x. So, I'm going to kind of skip that step. And now we need our initial condition, which is right here. we know that the particular solution passes through the points 0, 1. So now initial condition, y is 1, so 1 squared equals negative 1/2 0 squared plus c. Simple solution, c equals 1. So now plug in what you want, your c value. So y squared equals negative 1/2 x squared plus 1. And if you wanted to make it into the general form for an ellipse, you could add it in 1 negative 1/2 x squared over. So x squared over 2 plus y squared equals 1. That's the equation for an ellipse, which you're going to find when you complete this little field and sketch a possible solution. So go ahead and finish the rest of example 2, look at example 3 in the next page, check your work with my complete notes online.